Hey guys, welcome to lecture number 15.4. So last time we've talked about sequences of functions and how to deal with these sequences of functions when we have problems in taking the limit of an integral. We have seen we talked about uniform convergence. Also, we have seen the dominated convergence theorem. So we relaxed the condition of uniform convergence of a sequence of functions. And we said that in today's lecture, we will be talking about improper integrals. And I'm not just going to talk about only about improper integrals. I would also like to see a version of the dominated convergence theorem for improper integrals. All right, so let's get started. So again, I will just start with some easy examples. Well, first we'll start with what an improper integral is, and then we'll deal with some easy examples of convergence of conditionally convergence of an integral or absolute convergence of an improper integral and so on. And we'll see a bunch of examples. All right, so first let's consider if I have a function, let's say f, and let's just define on this interval AB, closed at A, open at B. So let's consider a continuous function. So if f is continuous, right? But let's say b is positive infinity, right? So we're going to take, or b is finite. But f is not continuous at the point B. If I have such a function, so once again, if I have a continuous function on the interval AB with the closed at A and open at B, and B can be infinity or finite, but f is not continuous at B, then we define the improper integral by the following, and I'm going to define it the following way. So let me put this, let's say this is 1. So this will be the integral from A to B of f of x dx, will be the limit as, let's just say x approaches b minus, right? From the integral from A to x, actually no, t, let's say. T approaches b, here t, of f of x dx. Provided that, so provided that that the limit exists, right? And is finite. So that's what we call an improper integral. So we're taking the limit as t approaches b from the left. And actually we can put something like this to emphasize this. b minus here. Well, we can say if this is the case, right, we say that that the integral above converges, or we can say that that's what we call conditionally convergence. So we say converges simply, or let me put here conditionally. Now, if the limit let me write it in this way. In fact, I don't need to. If the limit, let's just say the integral from a to b of the absolute value f of x dx is, as t approaches, let's say, b from the left, right? From the integral from a to t of f of x dx, an absolute value, right? So if this limit is finite, right? So if this limit is finite, we say that that the integral in one, we say that this integral converges absolutely. Converges absolutely. All right, so these are the definitions, right, of the uniform, of the conditionally convergence and the absolute convergence, right? And now, well, the question is, in general, which one implies which one? So that's the question. So absolute convergence will imply conditionally convergence, or the other way around? Well, it's pretty obvious that absolute convergence will imply conditional convergence. So let me point out this remark. So remark, absolute convergence will imply conditionally convergence, conditional convergence. But not the other way around. So the other way around doesn't work. Once again, I would like you to look at the two definitions. So it's pretty obvious that absolute convergence will imply conditional convergence, but not the other way around. So vice versa is not true. In fact, let's see why is that, and we'll give an example. So the counter example is the following. So let's just take this as an exercise. Let's just say that the integral call this I, which is the integral from 1 to infinity of sine of x over x dx, converges conditionally but not absolutely. So that's one example. I'm sure there are plenty of others you can come up with, but this is the first example where you can see that conditional convergence does not imply absolute convergence. All right, so let's deal with this one. Oh, this is not, this is a pretty simple example. Well, let's just deal with this integral. So we would like to see the convergence. So as you can see, you have the two functions here. You have sine of x over x, right? So so we have that this integral. Just say that. Let me take the integral from 1 to t, let's say, of sine of x over x dx. This can be expressed in the following way. Is the integral from 1 to t of, let's do, we'll do integration by parts. So negative cosine of x prime times 1 over x dx. So this guy would give us negative cosine of x over x from 1 to t minus the integral from 1 to t of cosine of x over x squared dx. All right, great. And we can proceed with the computations. So this would be negative cosine of t over t plus cosine of 1, right? And now as t approaches infinity, right? We're going to take t to approach infinity. This guy will go to cosine of 1 because as t approaches infinity, it's pretty easy to see that this guy will go to 0. All right. So in other words, we say that the integral let's say the integral from 1 to infinity of cosine of x over x squared dx converges because it converges absolutely. Converges absolutely. Well, why is that? Well, it's pretty easy. Well, you look at this integral, in the integral from 1 to t of cosine of x in absolute value over x dx, right? Over x squared, sorry. This will be less or equal than the integral from 1 to t of 1 over x squared. And this guy will, which is 1 minus 1 over t, which converges to 1 as t approaches infinity. Right, so this is, so therefore, it follows that my integral I is convergent. But pay attention, we have conditionally convergent, let's say. Now we show that there is no absolute convergence for my integral. Now we show that I is not absolutely convergent. So we want to show that. The way we're going to do this is in the following way. It's a bit tricky though. Well, So let me just look at this. So we're going to look at this integral. So the integral that from 1 to infinity of the absolute value of sine of x over x, right? So I'm going to take the absolute value, dx, and this will be greater or equal than the integral from pi to n pi, let's say, of sine of x in absolute value over x dx. Well, it's pretty, and now you can break this integral. So you take the integral, you break this into the integral from pi to 2 pi, then from 2 pi to 3 pi, 3 pi to 4 pi, and you do it in stairs. In other words, using the property of the of additivity of the integral. So this would be the sum from k equals 2 to n of the integral from, let's say here, k minus 1 times pi to k pi, right, of the absolute value of sine of x over x dx. And now we can say that this will be greater or equal than 2 over pi. And here you will have nothing else than just basically the harmonic sum, right? So, which as n approaches infinity, this will diverge. Let me just remind you the fact that the harmonic sum, well, it's almost the harmonic sum. It's missing the first term, but it doesn't really matter. It's just a constant. It's 1. So you can add and subtract 1. So there will be no problem with that. So, but let me just remind you that the harmonic sum diverges. In other words, the lim as n approaches infinity of hn is positive infinity, where hn is this guy here. Anyway, we've proved this. We've said, we talked about this when we dealt with sequences, so some time ago. So you can go back to that lecture if you want to see more details about it. So, but here we used, I want to, because I did not explain a bit, I like to use a little bit of an explanation. Well, how did we get all this inequalities here, right? So we use 2 facts, right? So remark in the so we used the fact that well, they're pretty obvious. So the first one was, okay, the integral from k minus 1 pi to k pi of sine of x in absolute value, dx is 2, and the second one that we used is that 1 over x is greater or equal than 1 over k pi. For all x in this interval, k minus 1 pi, k pi, right? Closed interval. So I think it's pretty obvious at this point, right? So this is an example of an integral that converges conditionally, but is not does not converge absolutely. Okay, and there are plenty of other examples you can come up with. But now I want to veer towards the integral because to talk about something that that would be, like I said at the beginning, this would be like a version of the dominated convergence theorem for improper integrals. And we will use this version for applications. So theorem. So we call this the dominated convergence theorem. For improper integrals. All right, so the statement, so let's say negative infinity b less than a less or equal than b less or equal than infinity. So we will allow positive infinity, and let a function f defined like we have previously seen from the interval ab, close at a and open at b, and this will be a real value. So be a function, and let fn defined on AB, right, a real values as well, be a sequence of functions, be a sequence of functions of course n is greater than 1, such that the following conditions are met. Are true. All right, the first one is that, and in fact, maybe I should say that it's, and I will explain this a bit, and maybe I should have explained this before. I would say Fn is integrable, but maybe I would say Fn is local integrable, because, you know, F is not defined on a compact interval, but I want to make sure that my sequence of functions, so Fn is local integrable on any compact subinterval, right? So on any closed and bounded subinterval. Anyway, I'll specify this. So Fn is locally integrable on AB for all n. So let me just explain this a bit. So I'll explain this. So if this means that Fn restricted to any, let's say here, compact interval. So the restriction to any compact interval is integrable, is, let's say, Riemann integrable. All right. Then the second condition is that Fn will converge pointwise, right? To so the limit as n approaches infinity of Fn of x is f of x. So in other words, this means that Fn converges pointwise, right? For all x in AB. The third one is that f as well is locally integrable. Right? On AB. And the fourth condition, and I may just, because let me write it like this, the fourth one, there exists a function And let's just say this function g defined in the same way. And let's just say that this is a non-negative function, right? Which is locally integrable. Right? There exists a function which is locally integrable on AB such that the improper integral, and I'm gonna write it like this. So the integral from a to b minus, right, of g of x dx, right? This is the limit as t. Let me remind you that this is the limit as t approaches b from the left, right, of g. The improper integral is convergent. Right? And of course, we have this condition that that we used to have in the dominated convergence theorem, that the sequence of functions fn in absolute value is less or equal than g of x, than the function. Basically, we can say that the sequence fn is dominated by g of x for all n greater or equal than 1, and for all x in AB. All right, if these four conditions are met, as you can see, well, the first three are just basically common sense, then we can say that then the improper integrals so the integral from a to b minus of f of x dx, and the improper integral from a to b minus of the sequence fn of x dx, right? These two, so these two improper integrals are convergent. Right? And moreover, we can pass to the limit inside. And the limit as n approaches infinity of the integral from a to b minus of fn of x dx is the integral from b minus of in fact, let me write it with red so that so we have that the limit as n approaches infinity of the integral from a to b minus of fn of x dx. This is the integral from a to b minus of the limit as n approaches infinity of fn of x dx. And this will be nothing else than the integral from a to b minus of f of x dx. So of course, I want these two to converge, right? All right, so it's a pretty long statement, right? But basically, this is just the version for improper integrals. So it's the same theorem as yesterday, as last lecture, but this is for improper integrals. All right, and now we would like to see a bunch of applications. In fact, I will show you now plenty of applications. And in fact, I'd like to combine this, how many theorems are there? So at this point, we have the following tools. So we have that, we have the uniform convergence theorem, right? So that's the first one, when we have that that the sequence of functions converges uniformly to a function f, so definitely I don't have any problems impacting to the limit inside the integral. But like I said, that's a very restrictive condition, very restrictive. All right, if we drop the uniform convergence, when we only deal with pointwise convergence, we have seen that the theorem does not hold true anymore. But if we add some kind of a dominant condition, like fn in absolute value is bounded by some function, which its integral is finite, then we can have sort of dominated convergence theorem. But all right, so we have the uniform convergence, then we have the Arcellas bounded convergence theorem. Then we have the dominated convergence theorem, which is a general version of this, but we also have the monotone convergence theorem. So all these four theorems are pretty cool, and they're these are very strong tools and applications. And you have seen two applications yesterday. We'll see more applications today, but now I'm going to put all of them at once, and we'll figure it out which theorem to apply. All right, so let me start with the first one. So applications. And also in the recitation, we'll see many more. All right, so let's say problem 1 says the following. So let f define on 0, 1 and real value be a continuous function such that the integral from 0 to 1 of f of p of x dx is 0. And this holds true for any polynomial function of degree 3. In other words, for any cubic, p defined on 0, 1 with values in the same interval, right? Show that we want to show that actually the function is actually 0. Show that f of x is 0 for all x in 0, 1. So we would like to, this was actually a, let me point out, this was a Romanian National Math Olympiad, I think, in 2001. Pretty cool problem. Of course, you cannot use, you have to use as elementary tools as possible, but I think the official solution was something like you construct in a certain way the polynomial of degree 3, which we will do in as well. It was some, I don't recall it, to be honest with you, but anyway. But now let's consider an x naught. So let's say let x naught a point in 0, 1, right? Fixed and arbitrary, right? Now for any positive integer n, we consider the following. So consider the following sequence of polynomials of cubics. The following sequence of cubics. I'm going to denote this by p of n. Right? And this will be in the following way defined. So it will be Pn of x. And this would be 1 over n plus 1 times x cubed plus n over n plus 1 times x0, x naught. All right, so let's see, what do we observe about this? Because we know from from the hypothesis, we know that the integral, so let's write it, we know that what? That the integral from 0 to 1 of f of Pn of x dx is 0. So we know that, right? It's given in the problem, right? But now, on the other hand, let's do we observe any properties, any like for this sequence of cubics? Well, if you look at it, so clearly this is non-negative, right? But also this is less than, since than 1 over n plus 1 plus n over n plus 1. So it's less than 1. So it's between 0 and 1 as well. Okay, that's great. And we know that this is for all n greater or equal than 1. Basically, we know that this is bounded by 1. So by the, and we know that this is a continuous, f is a continuous function. So by the bounded convergence theorem, what do we have? We have that as n approaches in, okay, we have, so we have that the limit as n approaches infinity of what? Of, so we know that this is 0, so 0 equals the limit of the integral of f of Pn of x dx. And this would be, so the limit will come inside. So this will be the lim as n approaches infinity of f of Pn of x dx, right? Which is nothing else. So Pn of x, let's not forget that this is converges to what? As n approaches infinity, this converges to x naught. So this would be nothing else than just x naught. The integral of, from 0 to 1 of x naught dx, which is nothing else. So f of x naught is 0. Since x naught was chosen fixed but arbitrarily, since x naught was chosen arbitrarily, then clearly then f of x is 0 for all x. And that's it. So the main ingredient here was just the bounded convergence theorem, right? That was a first application. Now I have some other applications as well, maybe a little bit more complicated than this one. Again, I have also problem 2. Again, this was a Romanian National Math Olympiad in 2006. And in fact, in this one, I will make use of the dominated convergence theorem, but the version for improper integrals. So you'll see why. So the problem says the following: show that what was it? That the limit as n approaches infinity of n times pi over 4 minus n times the integral from 0 to 1 of x to the n over 1 plus x to the 2n dx. So this guy will be the integral from 0 to 1 of, let me write in this way, f of x dx, where f of x is nothing else than it's arctan of x over x, right? If x is in 0, 1, open at 0, close at 1, and 1 if x is 0. This is the problem. Right? So, well, like I said, the official elementary solution for this problem was something alongside like integrating by parts a couple of times, then estimating. As you can see there, if you look at that integral, you have some arctangent there. So you can integrate by parts, and you can split the integral from 0 to epsilon, and then from epsilon to 1, and then you neglect one of the integrals. But anyway, I don't recall the details. Well, I just have to do it by hand. Well, like I said, we would like to apply here integration by, we would like to apply the dominated convergence theorem. Right? All right, so let's see. So let's see. So let's just look at this, the limit on the left-hand side. So we would like to do that. So let's denote L, let's say, the lim as n approaches infinity. All right, and we try to make it work somehow here in this limit. So let's see, what can we do? So we have the following. All right, so okay, so this would be the limit as n approaches infinity. Now let's be careful a bit. So I'm gonna write this pi over 4 as the integral. So it's n times pi over 4, which is the integral from 0 to 1 of 1 over 1 plus x squared dx, right? Minus n times the integral from 0 to 1 of x to the n over 1 plus x to the 2n dx. Okay, and this would be, let's look at it a little bit more. So now, now, so this integral here, so let's look at it. It's very tricky. Okay, x over 1 plus x to the 2n, and now let's be careful here, n to the, wait, what am I? Okay, let me delete this n here, and x to the, oh, n minus 1 dx. Okay. So because now I like to do u sub, So this would be, and you'll see exactly what do I want to do. So this one, let me just leave it like this for a bit. And this guy, I'm going to do the change of variable x to the n equals u. So let me write it here. No, in fact, let me minus the integral from 0 to 1 off. So this would be u to the power 1 over n over 1 plus u squared. And this will be du here, right? Okay. Where we performed the substitution. X to the n equals u. Okay. All right. So as you can see, I'm trying to transform my sequence of functions in such way that I will try to make it look like a sequence of functions, right? Okay. All right, now let's see. So I can write this. Well, the variable doesn't really matter that much, so we have that L is the limit as n approaches infinity of here we have a 0 to 1, right, of 1 minus, in fact, n, sorry, times 1 minus, let me just go back to the fact, variable x, so x to the power 1 over n, everything over 1 plus x squared dx, right? So that's what we have. And let's just say here is 0 plus 0 if you want. All right, and now we can consider this sequence of functions. So let me look at this guy here. So let me consider this like an fn. In fact, no, that's f of x. Let me consider this a gn of x, right? So let me write it here again. So this is 1n times 1 minus x to the power n root of x, let's say, over 1 plus x squared. And if we look at this, so this is gn is defined on 0, 1, and real value. So that's my sequence of functions. And now let's see the pointwise convergence. So gn of x, so let's see. So what is the limit of gn of x? So as n approaches infinity, so the question is, first question, what is the limit as n approaches infinity of gn of x? So that is the first question we need to answer. So it should be something in terms of x. Okay, so it will be ln of x. So it will be so as n approaches infinity, that would be so gn of x. Let's write it again, which is n times 1 minus the n root of x. This will converge as n approaches infinity. And let's be careful here. Okay. So it's e so it's okay, so let's see. So it's e to the ln of x to the power 1 over n, which is here, minus 1. So you have a minus here. And I put here downstairs ln of x. Divide by over n. But I already have n, so I have to put ln of x. But this goes to 1, right? As n approaches infinity. Okay, great. So therefore, so here I use the fact that as un as a sequence goes to 0 of e to the power un minus 1 over un is 1. So, right, because I can write the n root of x as x to the power 1 over n, or e to the ln of x to the 1 over n, or e to the 1 over n ln of x. So I can do that. So this will converge pointwise to, so that will be a negative, so it will be negative ln of x over 1 plus x squared. So that would be my function g of x, right? So g is also defined on a 0, 1, close to 1, open at 0. Okay, great. All right, so now at this point, I identify the function. Now, the question is, right, because my intention is to apply the dominated convergence theorem, right? So if I have in mind to apply the dominated convergence theorem, right, for improper integrals, right, because here I have 0 plus 0, right, 0 plus, let's say. Sorry, let me, right. 0 plus, so my intention is to apply, so let's write here. So our intention is to apply the dominated convergence theorem for improper integrals. Right? So that's our intention. So let's do so. So we identify the function g. So we claim that maybe, well, we want, that would be amazing, that this function will dominate our function. I hope so. So let's see. So the question is, we show that gn of x is less or equal than, I don't need to put the absolute value since everything is in 0, 1. For all x in 0, 1, and for all n. So we want to show this. This is crucial. And if we show this, then we're in a very good position. So let's do it. So what do we need to show? So we need to show, so this will be equivalent with showing that n times 1 minus n root of x over 1 plus x squared is less or equal than negative ln of x over 1 plus x squared. Or if you want equivalently, we have to show that n times 1 minus the n root of x is less or equal than negative ln of x. And if we do all these computations here, at some point, anyway, I'll leave this to you, which is easy to prove. Because I don't want to deal with this, but it's a pretty easy to prove. It's just, yeah, you can actually write this as a ln, and at some point you'll have that e to the exponent, e to the power whatever, x is greater or equal than x plus 1. You can use that, right? But I'll leave this to you as an exercise. Pay attention, you know how they say that the devil is in the detail, so don't take this for granted. And now, since I have this, right? So now I have this. Now I'm wondering what's going on with the improper integrals. Also, the improper integrals so let's see which one. The improper integral, okay, of 0, 1 of ln of x dx is convergence, and of g of x. So both of these two converge. So by the dominated convergence theorem for improper integrals, we have that L, the limit as n approaches infinity from 0, integral from 0 plus to 1 of gn of x dx. So now we can pass the limit inside. So this would be the integral from 0 plus to 1 of gn of x dx, which will be the integral from 0 plus to 1 of g of x dx. All right, beautiful. And this would be nothing else than just the integral from 0 plus to 1 of g of x. What was g of x? Negative, okay. All right, so, okay, and from here we can integrate by parts. So this would be, what? Negative ln of x times arctangent of x prime dx. And now using integration by parts, this would give us, let's see, this would give us negative ln of arctangent of x from 0 to 1 minus, so then here we'll have plus, so this will be a plus, minus, minus, plus, so the integral from 0 plus to 1 of arctan of x over x, which is exactly our function, or right? So, and you can show that this is actually 0, so you don't care about this one. And I'll leave this to you as an exercise. So this means that L is nothing else than just the integral from 0 plus to 1 of f of x dx. And we're done. Right? It was a pretty nice problem. Yeah, it's a very nice problem, right? So we have to find the function that will dominate our sequence of functions, but after that, it was pretty straightforward. Anyway, it wasn't an easy problem, but still, it was a very nice problem and a very nice application of the dominated convergence theorem for improper integrals. All right, so now let me do so I have two more problems in my mind. So problem number 3. I think this was a CMOS in 2014. In fact, this is what we call kind of a Balkan competition for university students. If you want like a Putnam type competition, but only for universities in the Balkans. So basically Romania, Bulgaria, Greece, Bosnia, Herzegovina, Serbia, Montenegro, and so on. So the process is the following. So in fact, there are two problems into one problem, and it says the following, if I remember correctly. Let me see. There was some arctangent function involved, but all right. So there were two parts here involved. So the first one is the following. Show that the limit as n approaches infinity of n times the integral from 0 to n of arctangent of x over n, right, over x times x squared plus 1 dx is pi over 2. And the second part, which is a bit more difficult than this, find, which it was pretty similar to the problem that to the previous problem, the limit as n approaches infinity of n times the integral times this right minus pi over 2. We want to see the first estimate of this one. Yeah, I think that's the statement. All right, so let's see. We would like to have a similar approach to the previous problem. Well, the first part is pretty easy because we know exactly what to do. So let's see. Yeah, I don't even need any change of variables for the first one, so. All right. So let's consider the following sequence of functions. So consider Fn right, given by Fn of x is n arctan of x over n over x times x squared plus 1. And now I'm going to introduce here times the chi of x on 0 n. 0 open at 0, sorry. All right, so I have this sequence of functions. Well, clearly this converges pointwise to the function. So clearly, and I'll leave the details to you. Why is that? Fn converges pointwise to the function f of x, which is 1 over x squared plus 1. Right? Moreover, it is quite clear that, that Fn of x Well, you can say an absolute value, but we don't care because it's positive. It's less than f of x. That's pretty obvious. You just use the fact that arctan of t is less than t, right, for all t positive. So you can, in our case, t is x over n, right? So this holds for all n greater than 1 and for all x non-negative. Then we can apply, so by the dominated convergence theorem, right? For improper integrals. Well, we have seen an example yesterday. Well, I kind of did it for improper integrals, but anyway. So we have, let's see, what do we have? So we have that the limit then approaches infinity of n times the integral from 0 to n of arctan of x over n over mx times x plus 1 dx. So this guy is the limit as n approaches infinity of the integral from 0 to infinity of fn of x dx, which is nothing else than just, well, you pass the limit inside. And this guy will give us the integral from 0 to infinity of f of x dx. So now this was the integral from 0 to infinity of 1 over x squared plus 1, which is arctan, which is pi over 2. The first part was pretty straightforward. That's pretty standard. All right, we did something like this yesterday, very similar. But now the second part is a little bit tricky. So the second part will be a bit tricky. Maybe I'll save the second part. Maybe I'll save it for the recitation. I think it's better for me to do that. So in the second part, so second part, I will not forget about it. Let's save it. Recitation. Right. Here we have to do something with this integral. You see, I have, so this will converge to 0, obviously. And we have to do a bunch of computations there, maybe, I don't know. We have to consider a bunch of other integrals. But I will save it for the recitation. Now I want to do another problem. So I'll leave this here with question mark. And now another problem in the remaining time. So problem 4. It's a very famous problem in Bourbaki's book. So it says that given a non-negative integer k, find the following limit. So the limit as n approaches infinity of the integral from 0 to the kth root of n of 1 minus x to the power k over n, everything to the power n dx. That's a very famous exercise in Bourbaki's book that I would like to do. Well, again, I will do it in a little bit more general fashion. So solution. So more generally, we can take an arbitrary positive sequence of positive reals let's just say an, such that an is bounded by this kth root of n, right? And now we consider n such that the sequence diverges. Now we consider, we let this integral, let's say in, to be the integral from 0 to I to my sequence an of 1 minus x to the power k over n, everything to the power n dx. Right? So we would like to see some things about this integral, especially the quantity inside the integral, right? And let's consider the following. So consider the sequence of functions. Let's just say fn, right? And fn of x will be the following. So it will be 1 minus x to the power k over n, everything to the power n, times chi on 0 an, pay attention. In fact, it's close here, of x. Right? Great. Well, I'll leave it to you as an exercise, so it is easy to show that fn converges pointwise to this function f of x, right? And this f of x is given by what? Given by, it's e to the negative x to the k. I hope I'm not mistaken. Okay. Also, it is very easy as well. One can show that. So I'll leave this to you as an exercise. That fn of x is dominated by this f of x. Again, I'll leave this to you as an exercise. Well, it's pretty easy. You just basically use the inequality here. What inequality? Okay. E to the power u is greater or equal than u plus 1 for all u. Right? So this holds for all n and all x. All right, great. So f of x dominates fn of x. And now we're not done yet. We can perform a change of variable so that we can we can make our life easier with this integral. So by the substitution, x to the power k equals u, right? So we perform this substitution. We have that. Let's just look at the integral. So the integral from 0 to infinity of f of x dx. So let me look at this separately. So this would be the integral from 0 to infinity. So that would be u over n. So this would be e to the negative u times 1 over k times u to the power 1 over k minus 1 du. And if you recognize here, this is nothing else than just the gamma function. So it's 1 over k, let me write it. The integral of e to the negative u times u to the power 1 over k minus 1 du. And this is nothing else than just 1 over k times gamma of 1 over k. And this is gamma of 1 plus 1 over k, where gamma of x, which is given by this, is the Euler gamma function. So this is just a generalization of the factorial. So now it's quite clear once we apply the dominated convergence theorem. So by the dominated convergence theorem for improper integrals, we have that. So let's see, what do we have? So we have that the limit of our integral of IN, I'm just going to write it directly, is nothing else than just the integral from 0 to infinity of f of x dx, which is, as we have seen, is gamma of 1 plus 1 over k. And that's it. This is a pretty famous exercise in Bourbati's book. I wanted to do this because it goes along the lines with the other ones as well. All right, I think I'm going to stop here for today. So I have, I owe you a problem. So that was the second part from that seamless problem. Anyway, I didn't want to do too many computations today, so probably I'll leave it for the recitation. In fact, next time I will talk a bit about, again, I will come with integrals. I'll be talking about integrals again, but in this, in the next lecture, I'll be also talking about a series of functions and power series and how to deal with these two and integrals. Because we don't have to switch only the limits of integrals. We can also have the series, the infinite series of certain functions, and when dealing with integrals, we want to see how the two, how we can swap the two. All right, so that would be probably hopefully, well, maybe not that lecture and one more lecture, and then we'll go with and do only problems in the recitations. All right, thank you very much.